Okay, let's look at this bending stress formula a little bit closer, just to make sure you understand all the pieces of it. Again, it's going to change over the cross section of my beam. One part of the beam is going to be in tension, the other part of the beam is going to be in compression. The closer you get to the neutral axis, the smaller your bending stress value will be. Okay? The farther away from the neutral axis you get, the larger your bending stress will be. Okay? And it's the largest it'll be at the outside edges. So, M is simply the applied bending moment. Okay? C is, again, usually we'll take it as half the depth on a symmetrical section, or at least the distance from the neutral axis to the outside edge. It could actually be something less than that. You know, we typically take it to the outside edge. Why? We take it to the outside edge because that's where the maximum bending stress is. But could you find bending stress at some point that's interior of the beam? Sure you could. Okay? And I is, again, from earlier chapter, moment of inertia. Now again, pay attention to moment of inertia about which axis. Because again, like we talked about in the earlier chapter, you know, I can have an x-axis, I can have a y-axis. All right, so again, typically beams are going to be positioned such that they're bending about the strong axis, but you know, which a lot of people call the x-axis, but nonetheless, be careful about that. Now, the big thing that I'd say in this is, what units do you think bending stress should come out to be? What units did your other stresses come out to be? Things like PSI or KSI, or, you know, if you were using SI units, it might be, you know, kilopascals or something like that. Okay? But for us, yeah, PSI and KSI would be customary US units. Therefore, what I'll say here is watch the units. Okay? Your moment might be something like foot kips. But your C distance, a lot of times I'll say, hey, the beam's 12 inches wide and it's 30 inches deep. Well, okay. If it's 30 inches deep, maybe my half the depth would be 15 inches. Then if you look like in the back of your book, you know, or calculate moment of inertia, what was the typical unit for moment of inertia for a lot of the stuff we did back in several chapters ago? Well, the unit was like inches to the fourth, right? That was very common. So, you know, you might have 350 inches to the fourth. Well, look at these units here. What problem am I going to have? I got foot, kips, inch, inches to the fourth. Where's my problem? The feet. All right? So you better change this into inches. How are you going to change feet to inches? Multiply by 12. If you multiply that by 12 and get that into inch kips, now look what I got. Inches, or excuse me, inch kips times inches. What does that give me on the top? Inch kips times inches. What do I got on the top now? Inch squared kips, inches divided by, on the bottom, inches to the fourth. What happens is my square up here goes away. What do I got down here on the bottom? So what's my unit? What's on top? Kips per square inches, KSI. So again, watch your units when you use that formula. Now here's the other thing about the formula. You know, I just threw in some numbers here, you know, just throwing in numbers. But Where would you get the moment at, do you think? I mean, maybe you're given the moment. Maybe you got a problem and they say, hey, the moment's 100 foot kips. But what else could they do on a problem? Well, they could say, find the maximum bending stress for this beam, and it's got this load on it. If you've got a beam with a load on it, or loads on it, do you know how to find the maximum bending moment? Well, you better. You just got done with the chapter that was almost the sole focus of the chapter. Okay, so shear moment diagrams, the moment diagram, that's where, you know, that conceivably could come from. Okay, does that make sense? So watch your units on that. That's really going to be important.